Good afternoon, everyone. My name is Scott Lee. So I am a principal software engineering manager at Microsoft, and I work at Microsoft's Core OS group working on Windows. So today, Chet and I are going to be sharing about CXL memory support and Windows. So in today's talk, we will be covering CXL memory and Windows. We'll talk about the virtualization that we are planning for CXL memory. Then we'll cover the Windows CXL memory architecture. And then we'll go through the various RAS workflow that we are planning for CXL memory. And then to end this talk, I will share about the current status and then the futures in terms of what are the other things that we are interested in going forward for CXL. So for today's talk, I will be doing the beginning and the end, and then Chet will come and talk about the memory architecture and then the RAS workflows. For CXL memory, the way we view CXL memory in Windows is we view it as part of the general problem of how do we support multi-tier memory in the OS. So in general, there are two approaches for CXL memory usage. In the first approach, CXL memory can be used as general purpose memory, or I use the term GP for short. So when CXL memory is exposed as GP memory, our expectation is that the memory is in memory-only NUMA nodes. And then given when the memory is exposed as GP memory, this is memory available to any of the current software that's running in the OS. So from a default OS memory management perspective, the allocation of memory is always from the closest NUMA node. So in general, there is no software change needed to use CXL if it's exposed as general purpose memory. But to get the best performance, you do want to optimize your software to be NUMA aware. The second approach where CXL can be exposed in the OS is as specific purpose memory, or for short, SP memory. So like GP memory, if CXL is exposed as SP memory, our expectation is that the memory is also exposed in the memory-only NUMA node. Memory that's exposed as SP memory are meant for specific usage. So in general, for memory that are exposed as SP memory, you can't allocate that memory unless it's done through new APIs. For optimizing and using SP memory, our expectation is that software will change itself. It will make changes to itself to basically place the data in the right type of memory. So in general, the memory that's exposed as SP memory are memory that have different characteristics than like the DDR memory that's common today. In Windows, we call specific purpose memory dedicated memory. So in the future, if you hear the term dedicated memory, it basically is the same as SP memory. So within the Windows OS Manager, we have made changes to our OS Memory Manager to be able to use SP memory. So some examples of where the OS Memory Manager may use SP memory is as a page file, or as stores for compressed pages that the Memory Manager does, or to hold data of recently used memory pages that are not currently in use. Within Windows, we are prioritizing OS first RAS handling over firmware first. And in the future, you should expect that within the Windows OS itself, you will see a built-in Windows driver for the CXL Type 3 devices. So at a high level, I would say that Windows and Linux are fairly aligned in how we view CXL memory, but there is one difference, which is how we support SP memory. The way SP memory is supported differs between Windows and Linux. Within Windows, the SP memory, the way we view SP memory is that there is a potential that a system can have many different types of dedicated memory types. So we've designed our support to be able to support an arbitrary number of different dedicated memory types that could be present on the system. So the way we view a dedicated memory type is that it has a unique combination of attributes. So the current attribute that we associate with dedicated memory is read and write latency and bandwidth. So we do expect that the number of attributes that uniquely defines a dedicated memory type to grow into the future, and our design can accommodate that. So in terms of the performance characteristics of memory that we track dedicated memory on today, it is based upon the speed of the media outside of any intermediate caches. Within Windows itself, we have introduced new APIs to be able to support dedicated memory. So these are through our existing memory partition and virtual alloc APIs in Windows. So a memory partition can have both regular memory and dedicated memory. And we have APIs that are available for folks to enumerate, to allocate, and to free dedicated memory. Besides this, we are also planning on introducing new Win32 APIs that makes it easier to work with memory-only NUMA nodes. So these APIs will expose, some of the things that these APIs can do is that it can expose the attributes that are exposed through the ACPI HMAP table. We'll also have API that allows software to discover what is the closest initiator node. So these are nodes with CPUs on it. So that if software wants to schedule work, it can figure out where, on which CPU it needs to schedule the work to get the lowest latency to the dedicated memory. From a virtualization perspective, we don't currently see any need for us to virtualize CXL memory devices to a VM. We believe that we can virtualize the usage of CXL memory into VMs using just the generic reporting of memory as either SP or GP memory. We will be building support within our hypervisor, which is Hyper-V, where at VM creation time, as you're creating a VM, you can specify for memory whether you want to expose that memory as GP or SP memory, and whether you want to expose that memory in memory-only NUMA nodes or not. So in the next few slides, we're going to go over the architecture and the RAS workflow that we are building, and Chet will be talking about this.
Thanks, everyone. I'm a principal software engineer also working on CXL. And so I wanted to go over kind of the high-level architecture that we're utilizing. And I kind of like to point to this. Can I just take this? Yeah, can you hear me? So I'm showing an architecture stack here with CXL down at the bottom with my CXL memory devices. Right, the platform connects our CXL devices to the root port, which is associated with a root complex, and all of that is platform-specific implementation is how that's done. What's surfaced to the OS are a number of ACPI and UEFI tables. For one thing, each root complex is associated with an ACPI 0016 CXL host bridge device or object in ACPI space. And the platform itself and the interleaving hardware that's involved is associated with a single ACPI 0017 CXL root port device or CXL root device. Attached to these ACPI objects are a number of tables. There's a CXL early device table, which contains the CHBS, which describes where the registers are for the root ports. And then under the ACPI 17 device, we have the CXL fixed memory window structure, which describes in a generic way the capabilities of the platform interleaving. So all of that, then we have the Windows stack on top of that, right? And we start with the CXL bus driver. It's going to enumerate the PCI CXL hierarchy underneath. It handles root port level functionality, and link and protocol error handling is all handled through the bus driver. It surfaces physical device objects for each of the memory devices that it finds in the hierarchy, and then we load a separate instance of the CXL memory device driver on top of that. The memory device driver is loaded for each type 3 device. This is type 3 only that we're talking about here. And it basically, essentially is communicating to the memory device using the component command interface, or CCI, which is a fairly simple mailbox mechanism for sending requests and getting responses back. What we do with this driver is we handle alert configuration, setting up the device for which alerts we care about, event record handling and interrupt configuration, right? We have to set up MSI interrupts. I'll talk more about OS first in a minute and what that means. It also sets up it does event record reporting. So as we'll see in some of the RAS flows, events are going to come up from the CXL device, and the MSI is captured by the memory device driver and handled completely inside of that. Events will get pushed up the stack from the device driver, and we'll talk about that in a minute. We also have what we call poison list harvesting. So at the beginning of time, the memory device, well, at any point in time, the memory device maintains a list of bad locations, right? Errors, places where there's uncorrectable errors. It's done on a cache line basis. So another thing we do is at the beginning of time, this driver will harvest any poison list that's on the device, and then we'll offline the memory, and I'll talk more about that in a minute. And then also handling device status register. So the device status register tells you if the media is ready, if the mailbox interface is ready, if the firmware is halted. Those things are all also handled by this driver. Thanks. All right, so moving further up the stack. So on top of the memory device driver is our memory bus driver. This is kind of our system level CXL functionalities are here. So the memory bus driver, in conjunction with the ACPI 17 device and the fixed memory window structures, the SRAT and the HMAT, and the memory that's being surfaced by each of these memory devices is kind of all contained in the bus driver, and it understands all of the interleaving. It handles, and because of that, it has to handle our device physical address, DPA, to system physical address, or SPA, translation. So anytime we're going to get like memory level events from the device that have a DPA associated with them, this memory bus driver is going to be the one that's going to translate that into a system physical address that the rest of the system can understand and act on. So it consumes those tables. And so it's going to report errors. Errors coming out of the memory bus driver go to our Windows hardware error architecture components that essentially are going to handle the event, and then basically, I forgot to say, the memory bus driver is going to produce CPER records, and CPER records are consumed by WIA, and WIA may actually add to the CPER record. It's going to act on it in most cases, potentially offlining memory if uncorrectable errors come up. WIA can immediately offline the memory so that it doesn't get utilized. And it's going to interact with the OS memory manager to do that. And then also the WIA will generate cell logs too, which is the system event log. So WIA out of the top of WIA will come CPER error sections and cell log entries. And then on top of that, you've got apps that are sitting on top of the memory manager. It could be Hyper-V, it could be other kinds of apps, monitoring software, just very generically. These events are consumed by other components inside of Windows to monitor what's going on and potentially take action. And I'll show you some examples of that when we go to RAS. All right, let's talk a little bit about RAS and OS first RAS. What do we mean by OS first? Well, in general, it means that instead of the platform firmware handling all of the events and reporting them, we are going to get the events directly in our memory device driver and act on those via MSI, MSIX. And so some of the RAS things that we're concerned about, unconsumed memory errors, memory module events, and I'll talk more about these in a minute. And these are all detected through interrupts that are generated by the device directly to the device driver. CXL bus driver also has a part in the RAS flows. It's handling root, port, and bus-related protocol link errors. Those are handled by the bus driver directly and not by the memory device driver. So consumed uncorrectable errors are not really OS first. They go through the normal platform firmware machine check exception architecture in general, including viral. So that's sort of kind of the standard way of doing it, not really OS first, but the rest of this is OS first, where we're going to get interrupts specifically and handle them directly in Windows. And then WIA handles the hardware events. Again, the events are conveyed through CPER error records, and it will offline 4K page size or greater depending on the error, and potentially crash the system, right? Bug check the system if it can't, if it can't offline the affected memory. Question?
Yeah, what was the reason for big OS bus on CXL here? Was it a position in the spec or was it more like the driver choice?
I mean, I think that's more our choice, right? I mean, the spec can do either one of those.
Yeah, I would say it's a choice that we made because we believe that OS has a better ability to deal with these errors. I know that some of our system OEM partners may disagree with us, but in general, from an OS perspective, we believe that OS first handling is better. So that's why we focus our energy first on OS first.
Yeah, I think it gives us more flexibility in being able to do whatever we want on the software side once we have that pipe directly for those errors. So, all right. Okay, so I'm just going to go through a few flows here, an example of some of the error handling we have to do. And the first set of errors are around, everything's driven by events in CXL, right? So we have DRAM/general media events. These are events that have a device physical address associated with a DPA. If you don't have a DPA associated with it, you're going to send a different event, and we'll talk about that in a minute. So in general, what I'm trying to show here is at the beginning of time, here's my memory device over there on the left side, my memory device driver, bus driver, memory manager, and WIA. But essentially what's going to happen in this flow is at the beginning of time, the device detects, say, a correctable error. And so it's going to generate a DRAM event record, fire an MSIX interrupt, and then our memory device driver will run, and in the interrupt handler, we'll go through a loop here of ingesting event records, pulling them off of the event log right directly from the device. And so we'll stay in this loop until all the events have been drained from the device. And so, what we're going to do is when the CXL memory device driver pulls in this DRAM event record, it's going to basically notify the memory bus driver that, hey, I got this memory error, and it's got a DIM or device physical address associated with it. The bus driver will perform the DPA to SPA translation because it understands the interleaving, it understands the memory map, and where this device plays in that memory map. And then we will the memory bus driver will build a CPER record with a memory error section and a CXL component event section. And I'll show this on the next slide. But essentially, there's several sections associated with the CPER record that's created. And that's going to get passed up the stack. In this case, it goes to WIA, right? And then WIA may output that CPR record and a cell log to upper layers of the stack. In this case, I just have a monitoring software component here. If the error was an uncorrectable error, then WIA can offline the page immediately. We want to take it out of circulation, right? As soon as we have an uncorrectable, take it out of circulation immediately. And so it's going to interact with the memory manager to perform that operation. And so the application sitting on top of the memory manager will be affected by that if they were using the memory. Yeah, and so for this general media events, DRAM event records, we generate the memory bus driver will generate this CPR payload. Inside of that is a CXL component event section. This is part of the spec, right? This was added in the early days of CXL. So what I show over here is a device with an event log, generates an event record. That raw payload goes into this event section, right? We just copy the event record payload so that upper layers of the stack have complete access to the original information. Then the bus driver will perform DPA to SPA translation, and then that SPA address, which is what the rest of the system really cares about, will go into a separate memory error section, and that contains the SPA address of the error. So this is kind of how we bundle up the event records, do the DPA to SPA translation, add another error section to the CPR payload, and then we pass that up the stack. And so WIA would act on the memory error section, take that SPA address, potentially offline the memory. But again, we also have the complete event record payload in case other portions of the stack or folks that are listening to these events can act on it. Yes?
Okay, so the question is, what happens if an application tries to access a memory location that's been offline through the OS memory manager? So the answer to that question is that if the application tries to access it, the application will get a page fault. So, right, yes.
All right, cool. So the next one are memory module events. So these are events that occur where we don't have a device physical address. It's not the event isn't associated with a particular memory address. There's a number of examples of this: temperature change, media status change, data path error, general data path errors, power management faults, performance might be degraded, hardware replacement might be indicated by the device. These will bubble up as a memory module event. There is no DIM or device physical address associated with it. So in this case, it's a very similar path. The memory device driver is going to retrieve the event records, and it's going to report the event to the CXL memory bus driver. The bus driver will filter the events and looking for ones that are unique or that require the device memory to be removed. A number of these are probably events we can just report and toss out and not have to act on them. However, if we decide that, hey, this is like a fatal error, I've got to offline all of the memory for the device and potentially offline all of the memory for the entire interleave set. If this device is part of an interleave set, a critical memory module event happens, we're going to have to offline all of the address associated with it, including, the blast radius includes the entire interleave set in that case. And so the memory bus driver is going to do some filtering and decide if this error warrants taking all the memory offline. And then it will determine the SPA address range is affected, as we talked about before. And then it's going to build a slightly different CPR section that contains a list of ranges that may need to be offline and report those to WIA. And then WIA will, as we said, may add additional error sections to it. We'll talk more about that in a few minutes. And then it will offline the ranges, if applicable, and generate cell events. And so it's a slightly different, similar flow. What the memory device driver does is pretty much identical. It just harvests the event, pushes them up the stack. Yeah, and so from a CPR payload, what this looks like is we have the CXL component event section. We always have one of those, and we just dump the raw payload from the event record into it, right? And then, so the bus driver is doing this. It's allocating space for this CPR payload. It copies the payload into the event record payload into the event section, and then it adds a CXL memory range error section with a list of SPA ranges to be offlined. So this is how we're going to handle having to offline not just a single cache line, not just a single 4K page, but an entire range of pages that, like I said, could include the entire interleave set potentially. All right, so the next class of errors are protocol errors, and these are usually through AER, right, through the AER handling. And so the bus driver is typically the handler for these kind of errors. And so the bus driver will receive the AER MSIX interrupt. Now in CXL 3.2, I think we have this RD pass structure where the bus driver can go out and it can figure out the address ranges for the type of protocol error, whether it's CXL.io or CXL cache mem errors, and then the bus driver will do different things. If it's CXL.io, this is just stock PCI. It's going to go out, read the PCIe error registers, write the error status to clear it, read PCIe error status registers, right? Read a number of registers out of PCI. This is just standard AER handling for PCI. If the RD pass structure says this is a cache mem protocol, then basically we're going to read the CXL RAS capability structure. So there's additional, this is predominantly our bus driver is pretty much our PCI bus driver with, CXL additions, right? It's CXL aware. And then so this is the CXL specific handling that it would have to do. Yes?
So this is the link, does it attempt to do a reconnect to complete the operation?
No, I think the question is, if it's not a critical error and the link goes down, will we attempt to bring the link back up and continue operation?
So is your question around a correctable link error or an uncorrectable link error?
Well, that was part of the question.
Yeah, like error, fatal
if
error.
If it's correctable, you just reestablish the link and
Correct.
keep going.
Yes.
And you do that.
Yes. Yes.
You don't even have to reestablish the link.
I mean, right. So
Still up.
Right. So in terms of like correctable link errors, I think there may be some that doesn't require any software intervention, that it'll be automatically handled by the root port, but there are others that may require software intervention, and in those cases, yeah, our bus driver will do the right thing to recover.
Yeah, we may have to do a function level reset, right, of the device, or there might be some other handling to do there that I didn't try to show here. And then so the outcome of this is you gather all this. AER is really just gathering a bunch of error record data, right? And then we're going to build a CPR record with a protocol error section in it. Again, we don't have an event record for this, right? So it's not, the CPR payload will look a little bit different, but it's similar. We're going to build a CPR record. We're going to report it to WIA. It gets reported to other places in the stack. One little wrinkle is that we added a completion callback, basically, when AER completes from the bus driver, and this basically gives the memory device driver that understands the device it's talking to the chance to check the device status and make sure the firmware hasn't halted or something like that. In other words, we can do device-specific handling in this callback if needed. And then I just show at the bottom, error non-fatal, sort of your question. We're just going to continue operation. If it's a non-fatal error, essentially the link is healthy, right? You don't have to reestablish the link. If it's a fatal error, we typically will bug check and not try to move on. You could do a lot more advanced error recovery down here probably, but typically today we don't. Yeah, Lee.
So you're saying you're doing system malloc, so is there a CXL specific EW channel that you're reporting through?
Can you repeat the question?
Sorry, so usually, we've got the different event trace channels.
Right.
Is there a CXL specific event trace channel?
So the question is, within Windows, do we have a CXL memory specific, I'm going to call it logging channel? And the answer is yes. Our CXL memory device driver does generate events automatically that will be logged into one of the log files within Windows. But earlier when we said that there is another system event log that's in the BMC. So that is through the IPMI interface. So our WIA component, when it detects errors, it will also generate a BMC system event log entry.
There's several cells floating around here in this discussion. All right, we can move on. Other question? Yeah.
So, yeah, when you mention bug check, so do we have a specific bug check for CXL event, or is it going to be on the way of bucket, like 24, and 124? And on the address translation, because if you're debugging, I want to, if a page is backed by CXL, or the CXL device, or regular memory device, do we have a different address pattern, or we just go sequentially as a virtual address?
Okay, so the question is, if the system crashes because of some CXL related errors, what type of sort of crash code will we see from Windows? So from a WIA perspective, the WIA component within Windows, whenever it crashes the system, the code it uses is hex 124. So as part of the parameters to the bug check code, it does also include a pointer to the CPR record. So from the crash, we are able to know, okay, this is a hardware-related error. And then from one of the parameters to the crash, we're able to see what the CPR record is that caused that crash.
Basically, the same flow, but if I have a bug check that's not CXL related, but it's a page fault, like 50 or 0, and how is there a way to discover if that page was backed up by a CXL device?
So the question is for non-hardware related crashes, if the crash is associated with some memory location, is there a way to discover whether that memory location is from, say, DDR memory or CXL memory? We don't have anything easily discoverable, but within if a dump file was generated, from the dump file, we should be able to pull that information as long as the dump file is not like what we call a mini dump, which is a small dump file.
Yeah, that's I was asking because you traverse the past to past.
Right. Yep.
But it's just a flat address, but then you have to go to the real point.
Right. So within the CXL memory bus driver, we do keep track of what is the system to the device physical mapping. So from some internal state, we are able to determine for a given memory address, as long as we can figure out what the physical memory address is, we'll be able to tell, is that memory from DDR memory or is it from CXL memory?
Yeah, so it's not completely obvious, but you can figure it out.
But you only have public symbols and you don't have other tools. So yeah,
Right.
quite over.
Did we skip? Oh, go back one, I think. Oh, no, okay, you're right. Okay, and so the last one I wanted to cover is poison list harvesting. And so at the beginning of boot time or device start, when our memory device driver loads, it will use a mailbox command and go out and get the poison list from the device. Some devices maintain a persistent poison list, some don't. Some maintain a persistent poison list across warm reboots, but not cold reboots. Either way, if the device is reporting that there's some bad locations, we want to know on every boot. And so if there is a poison list reported, we're basically going to build we're going to report the poison list to the bus driver, and then it's going to build a CPR record that contains ranges of memory that maps to each poison list entry. So the poison list is made up of a number of media error records, and we're essentially going to get a CPR payload that mimics those addresses. And so all of those would be offline potentially by WIA. All right. Yeah, and so I wanted to move on. We wanted to move and cover Intel flat memory mode because it throws some wrinkles into RAS. And so we call it FMM here in these slides, but it basically, Intel flat memory mode exposes a single address space containing 50% CXL and 50% DRAM. And the hardware controls the placement of the memory, right? And so we've talked in various events here today, this week, that basically about all the memory tiering. Well, this is memory tiering that the hardware is controlling versus instead of software, right? And so the wrinkles to RAS and the implications are the data could be found at two different possible SPA addresses, right? And so when events that require CXL memory to be offline will also need to offline the associated DRAM. You need to remove it from both locations so that you make everything coherent, right? Events that require DRAM to be offline will also need to offline the associated cache line and CXL memory. And so to handle this, our WIA component will determine what the extra SPA address is and add that additional memory error section. So if WIA comes along and says, we report an error to WIA, memory error to WIA, and basically it's going to look at a table that it's saved away of the SPA ranges associated with flat 2LM. And so when so in my little picture over here, I have DPA to SPA address translation occurring. We generate our memory error section. We generate our CXL component event section. But then we're going to add another memory error, we call a memory error extension section. That's basically where we're going to describe the other address, the other SPA address that's affected by this. And so in that case, the WIA is going to basically look at this SPA range information that it's stored internally. It's an ioctal it sends down and gets from the memory bus driver. But it's going to look at that table and it will figure out what the analogous DRAM SPA address is and add that. And then that gets pushed up the stack. WIA potentially has to offline 2 pages, 2 4K ranges to handle that. So it's one wrinkle that flat 2LM exposes that we have to deal with from a RAS perspective. Yes, yeah.
Not related to flat memory, but does the CXL bus drive support hot floods? Like now, since it's
So
devices, could add memory on the fly or remove memory on the fly?
So I think the question is, does the CXL bus driver, I think the CXL stack in general, do we support hot add and hot remove?
So as of today, we don't support it. And if you look at it from a hardware perspective of the hot add and hot memory, the hot add and hot remove, I think came in as part of really CXL 3.0. So CXL 2.0 doesn't support any hot add or hot remove. And our implementation right now is targeting 2.0 base implementations.
But do you, when you have a plan when you do 2.0 that you have hot add, how do you treat the PTE?
So as of right now, we don't have any support for hot add and hot remove. It is something for futures, but at this point, I don't know when we will consider it. Because realistically, I feel like hot add, while it is physically possible to do that for a memory device, I feel like it's too dangerous to do it.
It is. Yeah, but the idea of CXL in the future is to have that memory pool where you allocate and deallocate.
So definitely for cases where a system wants additional memory dynamically. I agree with you that in general, we feel like the best approach is memory pooling, not hot add or hot remove.
Using DCD, right? Yeah, using dynamic capacity, right? Remember, you're not actually physically removing the device. Then it's completely static when you bring it up, and then you're using extents to move memory around between them. You're not actually tearing the stack down. You're not doing a hot remove of the device.
But in this case, you would have to have like a maximum amount of PTs already reserved for
Yeah, that's
movement.
That's the DCD architecture, right? The device is going to report the entire max possible address space it would need. The OS at boot time is going to configure the or the BIOS will configure the HDM decoders to that max. And then DCD events, right, is where you're going to add and remove pieces of that memory, right, without having to tear the stack down, without having to do a hot remove. That's the direction we want to go in the data center or Windows, and not through mechanical hot add and hot remove.
From a memory management perspective, you need to have this already done, right? Even if you don't have the physical memory, but there is a possibility to have more memory.
You mean the add and remove?
So from a Windows OS Memory Manager perspective, it does support the ability to add and remove memory today. And that's what we'll be using going forward for supporting things like memory pooling.
Yeah, from other OS I had PT problems because when you do that, the PTs start growing because you have a limit, but this limit is so high that
Hopefully with DCD we don't have to worry about that, right? We're already set up to do the max, and then we're just moving data around within that maximum window that was set up. Yeah.
So part of your answer was CXL2 based, and so coherent. You're doing all your coherency management there in this environment. Then you think you'll
This is all HDMH.
validate, or is this all going to be controlled? This is all HDMH.
So in CXL 2.0, everything is coherent. Yeah. So we don't have to worry about coherency.
Yeah. Okay. So you don't anticipate using that in the future.
That's futures. I think if you hold off, I have a slide at the very end that talks about futures. Yes.
But yeah, I think in the future it's a possibility for sure. But right now it's all HDMH. It's all host coherent. Okay, what else? Oh, yeah, so a couple pain points. So we've been working with this for quite a while now, and we have these blades set up, and we're doing some pretty advanced testing with CXL. And we've come across a number of issues. And some of the early issues were where devices needed extra power, and it turned out they had an extra connector on their device, right? And it's like, it's not enough to plug it into a CXL slot. You actually had to jury rig and route extra power to the devices. So there was some struggles with that for sure. Platform firmware incompatibility, especially early on with these platforms. There's always incompatibilities, I think. So some of the things we struggle with. And then some of the implementations are not fully spec compliant. Some of the devices claim they're CXL 2.0, and there's some things where they're not quite, right? Or they do something that's 3.0, or, so there's some of those things you need to tackle, and I'm not sure that we'll eventually get there, right? I think as the ecosystem matures, a lot of those issues will go away. There's a number of spec gaps. I think between us and the other CXL consortium members, there are a number of ECNs that we're going to be bringing into the CXL spec to cover some of the telemetry, mainly, telemetry data, important stuff that when we're trying to stand up CXL in a data center environment, there's a lot of additional telemetry data that we probably need that right now is vendor specific. The spec, especially the CXL 2.0 spec, didn't specify any of those things. So that's been some challenging as well. And then minimal error injection, right? We want to be able to use CXL in-band and inject all of these errors I talked about, memory module errors, DRAM event records, inject poison so you can recover the poison list, being able to inject viral conditions or AER, all of that needs to come through CXL in-band approach. And right now we have inject poison and clear poison, right, which is very basic. And so that'll be something we'll need to improve on in the future as well. All right, Scott, it's all you.
So to end this talk, I'm going to share just a bit more information about where we're at in Windows. Right now, like I mentioned previously, we are working on supporting 2.0 or greater implementations with OS First Res with interested applications. Our initial focus is on memory expansion scenarios. So these are talking about direct attach CXL devices with no switch. We do have preview versions of Windows that folks, our ecosystem partners could try out and give us feedback on. This does require an NDA. The preview builds are available on the Collaborate tool that we use to share information about Windows with our partners. And the CXL support, the CXL memory support is available in both Windows Client and Windows Server versions. So we're not restricting the CXL memory support only the server. We're just making it a generic capability within Windows. As of right now, we don't really have a defined time period for when we will have official support. I think our focus right now is to build an internal Microsoft solution that uses CXL, where we can make sure that we have it working and working in a reliable way, in a way that's supportable before we consider officially supporting this in the Windows OS version. In terms of futures, like I mentioned earlier, we have server OEM partners that want firmware first. So as part of whenever we declare official support in Windows, we will add firmware first RAS handling. As mentioned earlier, we have strong interest in adding support for the dynamic capacity device feature that's in CXL 3.0. So this provides a capability for us to support memory pooling and memory sharing. So when we have hardware implementations available, we will work with our partners to add support for the DCD feature. We also have interest in supporting non-volatile persistent memory, because if I were to look at from a hardware perspective, we really don't have a bus outside of CXL that can support persistent memory. And we do have some niche scenarios today that are using persistent memory that we need to support going forward. So that is another area that we have interest in. And looking out further with CXL 3.0, security is very important to Microsoft and to the industry. So we do have plans on supporting the Trusted Execution Environment Security Protocol, or TSP, when folks start having support for it. And then last of all, I did put in hot add or remove as a futures, but I doubt that this will be something that would be very high on our list of things to do. I think we'll be able to find a lot of other things that are more impactful than hot add or remove. Okay, so I know that we've taken some questions that we've gone through the talk, but does anybody else have any other question? Okay, go ahead.
I have a question about your special memory. You mentioned something, you have an API that treats the special memory, and also you have a very nice slide to describe the entire software stack, right? The device manager. Where's the tapping point? Like, if I want to use that API, which box will tap me?
Okay, so the question is about the support in Windows of the specific purpose memory, or what we call dedicated memory, and what box here within the slide does that support come from? So the API is really part of our memory management support. So it's the OS memory manager that provides support for those APIs around discovering and allocating or freeing of what I call SP memory. Okay? The question is for the CXL memory support, does it, in terms of page size support, what does it support? Does it support only 4K pages, or can it support large page size? So we can support both for CXL memory. Okay. Okay, so the question is, what type of latencies can we handle from an OS perspective? I would say that the jury is still out, because if you look at all of the current implementations out there, they're mostly just DRAM based. So I mean, yes, I'm aware of several companies that are working on, I would term hybrid device, where you can have a device that has a DRAM cache with a NAND backend. And definitely for those types of implementation, I do have some concerns about what is the latency going to look like if you have a memory read that doesn't hit the DRAM cache. So I know that is a topic that several companies are thinking about. And recently, folks have come to me and suggested, hey, can we do this? Can we try this idea out to deal with this problem? So this is an area, I would say, an area of interest, and an area that we'll think about some more going forward. So. I can add in a future version of the slide, yes. Right. Okay, so I think our time is up. And thank you everybody for attending this talk. But definitely, if you have additional questions, yeah, feel free to talk with Chet or me after the talk. But I won't be available after this talk because I have another talk that I have to go to. So thank you, everyone.